This video is about to find the maximum and the minimum for the functions depend on two variables. Before we talk about how to find the maximum and the minimum for the function depend on two variables, let's recall what we did before. How do we find the maximum and the minimum? So function depend on one variable. So if I give you function y equal to fx and I give you domain interval ab, so how do we find, for given x in the interval ab, you have fx. So for all the x in ab, how do you find the largest fx and the smallest fx? This problem sounds like impossible because we try to compare infinite many numbers, infinite many fx. However, if you look at the graph, if remember y equal to fx give you a curve. Okay, here is A, here is a B. Okay. Now we want to find the largest and the smallest. Okay. So in this case, if we know the graph, obviously the largest fx is fb, right? The smallest is this number. Okay, we give a name. We call the summing points are important. Like this one, we call it x1, and this is x2. Okay. Now, we call fx1 local maximum because locally fx1 is locally the highest point. Okay. And the fx2 is local minimum. But for this case, it's also the lowest point for the whole fx on the interval ab. So fx is a local, fx2 is a local minimum and also absolute minimum for this case. So look at this graph. For all the points between a and x1, there's infinite many points. You don't worry about them. They are not going to be maximum and the minimum. Okay, neither. So look at this graph. What we need to do is what? Find your maximum and the minimum. Only could happen at what? At those x1, x2. What is x1, x2? Local maximum and local minimum. And also could happen at what? Boundary. So for this case, what you need to do is find what? fa, fx1, fx2, and fb. You really need to compare just 4 points. The largest one will be your maximum, lowest one will be your minimum. Okay, now how do we find x1 and x2? They are local maximum and local minimum. Let's look at it. At the local maximum, we have what? Your slope of tangent is horizontal. So is for local minimum. Therefore, to find those local maximum, local minimum, what we need to do is what? What do we mean horizontal tangent? That means your slope of tangent is 0. So you need to find f, take a derivative, set it equal to 0, find x. Remember we used to call x is a critical number in the count 1. Okay, so the procedure to find absolute maximum and the minimum for the curve is find all those critical numbers. In other words, those x make your derivative equal to 0. Okay. Or does not exist. And find those numbers, then find the two endpoints, then find the function values. The largest one will be maximum, smallest one will be the minimum. Okay, if you understand the function depends on one variable well for the maximum and the minimum issue, then we can do similar things for the function depends on two variables. Okay, I give you function depends on two variables. How do we find the maximum fxy and the smallest one for the given domain? Same sense, we need to find what? Local maximum, local minimum. Okay. Function depends on two variables. That means what? Is a graph is a surface. That's what the most important sense you need to know. It's a surface. Okay. Think about this point is a local maximum. X, Y, and Z. This is surface Z equal to fxy. Okay, this point say x naught, y naught. Okay. Now, let me say that again. This point is a local maximum. Okay. Here is a y naught. Here is x naught. Remember, if you let y equal to y naught, which is a plane, go up, intersect your surface, you got what? You got a curve on the surface. Okay. Since this point is the largest one locally on the surface, there must be what? Local maximum on this curve, right? So the local maximum for the curve, what happened there? They must have what? The slope of tangent must be 0. Okay. What is slope of tangent for this curve? Remember, that's exactly what? Partial f respect to x. Okay. Again, this point is local maximum on the surface, so there must be local maximum on the curve. Local maximum on the curve, that slope of tangent is 0. Partial f respect to x is slope of tangent for that curve, so it must be 0. Okay. Similarly, if you let x equal to x0, which is another plane, go up to intersect your surface, you got another curve. Okay. Again, this local maximum for the surface must be local maximum for this curve, right? Therefore, since it's a local maximum for the curve, then the slope of tangent must be 0, which exactly is the partial f respect to y. You fix x. Okay, so this tells you how do we find the point where you achieve your local maximum. Now you have what? Two equations. Now we can find the two unknowns, which is x and y. Those are just like the critical numbers we had before for the one-dimensional case. Okay, let me repeat that again. For the given function depends on two variables, which means I give you surface. How do you find the local maximum? To find the local maximum, you need to find the two partial derivative and set up equal to 0. Then you got the two equations. Solve x and y. Okay. Then you find the critical numbers. At those points, you may achieve your local maximum or minimum or nothing. Okay. So then we need a second derivative test. Okay, remember, for the one-dimensional case, this is x1, x2. We know x1 is what? At x1 you got a 0 slope. Okay. If without giving you a graph, how do you know fx1 is maximum or minimum? Now, that's why we have something called a second derivative test. Now, let's take a second derivative. Evaluate at x1. For this case, we have fx is concave downward at x1. Concave downward means your second derivative is negative. Okay. So if your second derivative is negative, it means your curve is concave downward. Therefore, fx1 is local maximum, local max. Okay. And at x2, your second derivative is positive, right? Because my curve is concave upward. Therefore, your fx2 is a local minimum. Okay, for the function depending on two variables, we also have second derivative test, but it's much more complicated. Second derivative test. Okay. The second derivative test, first of all, we have to find a quantity we called evaluated at point AB. Has been defined as fx second derivative with respect to x AB f y AB minus fxy AB square. Okay, first of all, we have this quantity d there. You need to find that out. Okay, then we have the situation. If d is a positive, fx second derivative AB, if that is positive, then fab is a local minimum. Second case, if d is a positive, fx xab negative, that means concave downward, then your fab is a local max. Third case, if d is a negative, then fab is not max or minimum. In this case, we called fab saddle point. Okay, this is similar to the case for the curve y equal to x to the third. Okay. At 0, you got a 0 slope, but at 0, your function is not local maximum, is not minimum neither. Okay, this point is really the saddle point for the one-dimensional case. For the function depending on one variable, it's hard for me to draw you surface. Okay. All right. So the second derivative test, you only test on those critical numbers. You don't test for any point. You only test those things that make your partial derivative equal to zeros. Okay, now let's look at the example. Now we want to find local max, local maximum, minimum, or saddle point for this function. Okay, for fxy equal to x to the fourth plus y to the fourth minus 4xy plus 1. Okay. Now I give you a fxy, that means I give you surface. Okay. Now we want to find the local maximum, local minimum, and the saddle points. Okay, remember how do we find those? To find the local maximum, local minimum, we need to do what? To find the two partial derivatives and set them equal to 0, right? So now let's find the partial f respect to x first. Okay, find the partial derivative with respect to x. That means you treat y as a constant. So the first term give you 4x to the third. Y is a constant. The second term is 0. Then minus third term treat y as a constant. Give you 4y. Okay, and set equal to 0. Then find the partial f with respect to y. Give you, this time you treat x as a constant. Give you 4y to the third minus 4x equal to 0. So we got two unknowns, which are x and y, and the two equations. Now let's solve those. We can divide the 4 from the first and the second equation. We end up with x to the third minus y equal to 0. Then y to the third minus x equal to 0. Okay, from the first equation we can say y equal to x to the third. Then plug into the second equation, we got x to the ninth minus x equal to 0. Okay, and this one you can put x out. Then you got x to the 8th minus 1 equal to 0. And x times x 8th, this is equal to 0, remember. Minus 1. This one can be factored as x to the 4th minus 1, right? Then x to the 4th plus 1. And can be factored further. X times x squared minus 1, x squared plus 1, and x squared plus x fourth plus 1. Okay, this whole sentence equal to 0. We're looking for x. Make this sentence equal to 0. Obviously, x equal to 0 is a choice. 1x equal to 0, you got a 0. And 1x equal to 1, the second term is 0. You multiply 0, multiply anything, give you 0. And x equal to negative 1. Also make a second term is 0. And x squared plus 1, x fourth plus 1, there will never be 0 for any real number. So that's our choice. Okay. So once you have x, you can find y. Okay. Remember, y is x to the third. Okay. So 1x equal to 0, you plug in there, your y is 0. That's one critical number, critical point. 1x equal to 1, you plug in. 1 to the third is 1. X equal to minus 1. Minus 1 to the third still give you minus 1. So we got 3 points. At those points, you may have your local maximum, local minimum, or saddle point. So we need to have a second derivative test. So we need to find the quantity d. Okay. So first of all, let's take a second derivative, fxx. So look at it here. Take a derivative on that, respect to x again. Give you 12x squared. Second term is y is 0. fxy equal to fyx, the same. Okay, look at the first equation. Take derivative with respect to y. Give you 4, right? Treat x as a constant. Okay, now let's find fyy. Fyy there, give you, take derivative with respect to y on the result of that. Give you 12y squared. Okay, now let's testing those points one by one. Okay, now first let's see d00, 0, which is fxx 0, 0, fyy 0, 0, minus fxy 0 0 square. Okay, fx 0 0 is 0. fyy 0 0 is also 0. Minus fxy square, 4 square give you 16. Which is negative. That means what? By the second derivative test, 0 0 at this point is what? Saddle point. Okay, now let's see D11. Fx x11 Fy y11 minus Fxy 11 square. Fx11 replace x by 1, you got a 12. Fyy11 you got another 12. Then minus 4 times 4 give you 16. Obviously is a positive. Okay. And fxx11 give you what? Equal to 12 times 1, which is a positive. That means what? Your curve there is a concave upward. By second derivative test, 0.11 is what? Local minimum. Similarly, you can check the point for -1, -1 is also local minimum. Right, it's also local minimum because you got x squared. Okay, now let's look at another example. Okay, now we have a cardboard. Okay, we have like cardboard. With like a 12 square meters. Okay, we want to use this cardboard to make rectangular box. Here is x, y, and z without lid. Okay, now what we want? So obviously you give a different x, y, z. Then you got a different you make a different box. I mean different box with a different dimension. The volume will be different. Okay. What we're looking for the dimension x, y, and z, such that this box, first of all, made of this 12 square meter cardboard. At the same time, the volume is the largest. Okay, so for those kind of word problem, the first thing you need to identify the quantity which you want to find is a maximum or minimum. For this problem, what we want to maximize the volume, right? So we'll use the V to denote the volume. V rectangular box, the volume is x times y times z. Okay. We want to choose x, y, and z such that the volume of the box is as large as possible. Okay. Ask yourself, can x, y, z be anything? If that is the answer, then this problem is easy. The volume go to infinity. Choose x infinite large, y and z infinite large. You got an infinite large volume. Okay. However, remember this box is made of 12 square meter cardboard. Okay. Remember this box without lid. Okay. So what do we mean by that? That means the surface area of the box must be 12. Okay. What is the surface area? Okay. Here is z. Okay. X times, here's z. X times z give you this area. X times z. You got two of them. Okay. One in this side. Then y times z give you two sides too. YZ. Okay, then you have the bottom, which is x times y. Remember, without lid, so x times y, you only got 1. Okay, this total surface area give you 12. This constraint just show you x, y, z, they cannot be anything. They must satisfy this equation. So if you solve from this equation, for example, I solve z can be written as 12 minus xy divided by 2x plus y. So then you can plug in z by using in terms of x and y. So you got things like that. 2x plus y, 12 minus xy. This one you can simplify that. Give you 2x plus y. Then you got 12xy minus x squared times y squared. Okay, what we're looking for, we want to choose x and y here. Okay. So now this problem becomes to what? Find the maximum for the function depend on two variables. Okay. How do we do that? First of all, find what? Local maximum and local minimum, right? Okay. How do we find the local maximum and local minimum? We need to find the two partial derivatives. Then set them up equal to 0. Okay, now let's find the partial v respect to x. How do we do that? Using quotient rule. Okay. So denominator square. Then put your denominator here. Take the derivative of numerator respect to x. Treat y as a constant. You got a 12x. Treat y as a constant. 12y minus 2x y squared. Okay. Then minus. Fix your numerator. Take the derivative of your denominator. Give you 2, right? Treat y as a constant. Okay. To simplify that, you got this. I'm not going to do that. Give you y squared 12 minus 2x y minus x squared. Similarly, you can find the partial f with respect to y. Give you 2x plus y squared x squared 12 minus 2xy minus y squared. Okay, so the next thing we need to do, always remember your goal. Our goal is to find x and y, make v as large as possible. So we need to find two partial derivatives and set equal to 0. So set them equal to 0. So we get, for example, your x equal to 0, this is equal to 0. That's not what we want. Okay. If one with dimension is 0, you don't have the box. Okay. So we can forget about that case. So the first equation will have 12 minus 2xy minus x squared equal to 0. The second one, you got a 12 minus 2x y minus y squared equal to 0. So if you use the first equation, subtract second equation, gives you minus x squared plus y squared equal to 0, right? If I use the first equation, subtract second one. So that's equivalent to say x squared equal to y squared. You can say x equal to y, okay? Remember x and y both positive. Then you put it back. For example, go back to that equation. You got 12 minus, remember y equal to x. So you got 2x squared minus x squared equal to 0. This really is 12 equal to x 3x squared. So your x there equal to x squared equal to 4, x equal to 2. Okay. Similarly, you can find your y equal to 2, you can find the z. So you find the, okay, you find the 2, 2, okay? X equal to 2, y equal to 2 is your maximum and the minimum could happen there. Then you can use second derivative test. And obviously, this one, you got the local maximum. In the other words, you can make, okay, once you know x, y, you can plug in, you can find the z. Okay. How do you find z? Remember, our z there, where's our z? Our z there equal to 12 minus 2xy divided by 2x plus y. Use that formula, you can find the z. You're going to see equal to 1. So, in the other words, if you make a box here, wait. Here x is 2, y is 2, y is 2, z is 1. Then you can check. If you use this dimension, your surface area is going to be 12. And at the same time, the volume will be the largest. Now, the reason we got this dimension because what? This box without lid. Okay. If the box with a lid, you can imagine for the fixed surface area, the maximum volume is what? X must be a cube.